In this lecture, I'm going to review the basics again of electron configurations, and I'm going to expand that discussion into excited states, ground states, the shapes that these wave functions actually, or the shapes of the orbitals actually exist in nature, okay, and also relate their valence and core electrons again, and go a little further than I did today in class, and really finish out this idea of electron configurations, which again is based on the principle of wave mechanics. You have to understand that we're talking about either something called wave mechanics, and that really means mechanics believes is mathematics, so it's mathematics of waves for electrons. Sometimes you'll hear it called quantum mechanics, okay, quantum wave mechanics. Now the reason why it's quantum is because just like Bohr started with this revolution, that electrons have discrete energy levels. Okay, now they didn't go in circular orbits, but they do move from one quantum state to another and nothing in between. And that quantum state is from one type of orbital to another. And of course, we have several different types of orbitals. So the first place I want to start is how do you know how many orbitals exist in each energy level? Well, first of all, in the first energy level, okay, which is equal to n equals 1, okay, sometimes it's the same thing as the row 1, we know that there's only an s. In the second energy level, where n equals 2, that's the second row, you have s and p. Third energy level, you probably guessed it, when n equals 3, you have s, p, and d. And of course, the fourth, n equals 4, you have s, p, d, and f. This is an important basic, because you should know that the actual energy level, the major energy level, okay, has the same number of sublevels. So the second energy level has 2. The third has 3. And this is, you have to understand, a product or a solution, okay, to the Schrodinger equation. The Schrodinger equation you're not responsible for knowing, but how we put or organize our electrons in an atom based on energies, discrete quantum energies, is based on these probable or wave functions that are based on probability. And they're three-dimensional, and they have shapes that I'm going to show you. So to first start is to know that the first rule is that the energy level, the major energy level, sometimes called a principal energy level, is the same thing as saying n equals 1. That's the first principal energy level. It's the first row. Okay, they're all synonyms, so it's important. The first principal energy level only holds 2 electrons, a maximum of 2. Why? Because the s holds 2. In the second energy level, because we know the s holds 2, and if you don't know, party people, as I've been talking before, this is called the s block. All right, so right here is the s block, and it has what? It has 2 columns to help you remind there's 2 electrons. Now the p block are these blocks right here. And if you count all of these blocks here, how many columns? You'll count 1, 2, 3, 4, 5, 6. And of course, the p's hold 6. Third energy level, 2 plus 6. Now the d block, of course, is right here. That holds, if you count the columns, 10. So it's all there for you. So if you want to count total number of electrons, okay, well, the first energy level, or the first principal energy level, holds 2. The second holds 8. The third holds 10 plus 6 plus 2, okay, 18. And of course, the fourth, 2 plus 6 plus 10. The F is down here, and you count the columns now. You'll count 14, and you put that together, and you'll get your 32. So these are the major number of electrons that exist, okay, that can be held maximally in these energy levels. Now, I'm stopping at 4 because the rule gets broken up. In the fifth energy level, you should know that there's what? There's S, P, D, and F. Wait a minute. The rule is the number of sublevels where electrons exist is equal to the number of principal energy level number. We're right. That's why there's actually a G here. But we actually don't fill the G up. Okay, the G would actually fill somewhere after 8s. So because we don't have enough electrons, the or have any electrons that are in their ground state, which means we don't have any elements that fill the 8th row, the G never gets filled, so we don't talk about that. But still, the rule is true. Now, the Schrodinger equation, okay, helps us define where electrons exist. And as I already talked about, you have to tell me where every electron exists. But now, there's another rule, if I haven't forgotten, is the 2n squared rule. 2n squared rule tells us how many electrons exist maximally in each energy level. So if I do this in the second energy level, n is 2, we square that, we get 4. 4 times 2 is 8. In the third energy level, that means n equals 3. 3 squared is 9. 9 squared is 18. And you see how that works nicely. Okay? Any case, those are some basics you need to have. Number of principal energy level equals the number of sublevels to know how many electrons each. Now, there's one little piece of this puzzle that people tend to get lost here, and that is the word orbital. Okay? Now, when I say orbital, that's where a pair of electrons exists. All right, so let me just white this out again. Whoa, I can do this. Okay, so I white this out, and let's just use this area here. So what does orbital mean? Okay, let's go over the organization. Again, these are just solutions, exact solutions to the equation where there's exact energies. So we have principal energy level, we have sublevel, which is S. Oops, I made a mistake. Let's put a white here. Oops, let's do back. Okay, we have sublevel, n equals 1. I can do this. So when n equals 1, we have a sublevel S, and in that S, we have one orbital. Now, what's an orbital? Orbital is a place where 2 electrons can exist, and you should know that an S sublevel holds 2 electrons. Okay, and sometimes they draw orbital notation to show that. Now, an orbital is a pair of electrons, so for an S, you'll see it as a box. If there's 2 of them, they'll show 2 arrows, and that's orbital notation. So if I have hydrogen, who is 1s1, okay, then I would put the box just 1 electron. And if it's helium, 1s2, 1s2, I would show 2 boxes filled. Then if it's lithium, it's 1s2, 2s1, I draw another orbital. A box is for each what? For each pair. Now, since electrons in S hold 2 electrons, 2 columns, we put 2 electrons there. Actually, 1 electron, sorry. Okay, 2s1. Now, if it's beryllium, 2s2, another extra electron. Now, if you notice, I'm drawing arrows up and down to show the repulsive nature. This is called spin, electrons going in opposite direction. We'll talk more about that Monday. Now, if I go to boron, don't B1, that's going to be 2p1. It's the first p block. And you should draw 3 boxes for boron. And you say, well, why? Well, there's 6 columns. And if the p holds 6 electrons, then there has to be 6 boxes. So if I was to do this correctly, and I'm, again, just going to make some room here because I can. All right. I would have to draw 3 boxes for the p's. Each box represents an orbital. All right. Now, if I get to F, which is 2p5, it would fill this way. Watch. 2p1 is boron, which I've kind of erased. All right. 2p2 is carbon. Notice they're filling empty boxes first. And then 2p3 is nitrogen. You may say, well, why are they doing that? Well, electrons repel themselves. This p right here holds 6 electrons. And electrons exist in pairs, in areas called orbitals. So this orbital is a box that we draw to show the notation of where electrons is. Since there's 6 electrons, and a pair is where electrons exist in nature called an orbital, there are 3 places, 3 regions, 3 wave functions. And these electrons are not going to pair up until they're forced to. Here they pair up because there's only one choice. When you're in the same sublevel, you only have one S. S only has 1 box, so the S has to fill. But P has what? Has more places to go. So electrons would rather go in an empty orbital before they're forced to repel. Therefore, oxygen, okay, would be a place where it first pairs up, and that'd be 2p4. Then oxygen, oxygen is 2p4, nitrogen 2p5, and then fluorine I'm sorry, not fluorine's 2p5 now, I'm sorry. And then neon, when it fills that orbital and everything's filled. Again, I'm showing the arrows going opposite to show that electrons repel themselves. Something called opposite spins. Okay, and then I go to sodium over here. 3s1, well, S only holds what? S holds 2 electrons. So, oops. S holds 2 electrons, so it gets 1 orbital. And S orbital only holds 2 electrons. So there's the 1. Magnesium, 3s2. And now we go to what? Aluminum, 3p. And guess what? You'd have to draw, again, 3 boxes for the p. There's 3 orbitals for the p. And you get the point. And if you keep drawing them correctly, remember, if you're in the same sublevel, you have to add electrons. This is called Hudd's rule. You have to add electrons into empty orbitals first of the same orbital. So 2p1, 2p2, 2p3, which is phosphorus, sulfur 2p2, sulfur 2p, I'm sorry, phosphorus 2p3, sulfur is 2p4 like we have, chlorine is 2p5, and then argon, you fill everything. And that's why it's stable. Now, d orbitals, because there's 10, how many boxes would you draw for the d's? And you would draw 5 boxes. Why? Each box is an orbital. An orbital holds 2 electrons. And why is it I'm drawing 5 boxes? Because there's 10. And if I look down yonder, the F's have 14 electrons. So that means there's 7 pairs. So I would need 7 boxes. And how would they fill? They would fill, my boxes are getting lazy. 1, 2, 3, 4, 5, 6. Okay, is my. How would they fill? They would fill empty boxes first before they pair up. Again, that's called Hudd's rule. We'll talk more about that. All right. Now, the thing is, my friends in chemistry, they're not really boxes. And the animation you see on my website shows this orbital notation. But this is one orbital. An orbital holds 2 no matter what you call it. Now, where is the orbital? This orbital I'm circling is a 3p orbital. It has 2 other orbitals, but this is the one I'm talking about. The one I'm circling here is one of the d orbitals. They all hold 2. But they don't have box shapes. They actually have 3-dimensional shapes. Let's go there. So this is a nice website called the Orbitron. Okay, search for the Orbitron. You can see that. I have a link for that. But this is 1s. S is spherical. This is a place for 2 electrons. An S sublevel only has 1 of these shapes. This is an orbital that's shaped. A 2s, okay, eventually, maybe. A 2s, okay, engulfs the 1s. It's farther away from the nucleus. This is the nucleus. This is the 1s. The 2s is also circular. And 2 electrons fill this region. This is 1 orbital. But 2p, or not to be, okay, has 3 different shapes. Why? Because there's 3 different boxes, right? Remember the 3 boxes we drew for P? 2 electrons fit here, 2 electrons fit here, 2 electrons fit here. These are 3 different orbitals. They have 3 different boxes. S only had 1 shape. P has 3 different boxes. You can guess what D looks like. 5 different boxes, 5 different shapes. And F, you have to draw this on a test, okay? Of course not. But F will look like this, maybe. All right, obviously you'd have to draw this for a test, but look at the shapes. 1, 2, 3, 4, 5, 6, 7. So this one holds 2, this one holds 2, this one holds 2. Different 3-dimensional shape. These are the standing waves that we've been talking about. Electrons exist based on probability. And in fact, there's also a G. What does that look like? Well, you can guess how many G's would have. G's would have, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. 18 electrons total in a G orbital. But again, that is, we have no elements that have that in their standard state. So let's just go through this one more time another way as we add electrons so you can visualize what you're doing, because this 1s2, 2s2 really is talking about the proximity of these types of shapes to the nucleus. Here we go. Okay, so here we go with the nucleus. Add a 1s, maybe. And here's a nucleus, and 2 electrons fit this orbital. A 2s, which is next, 2 electrons fit in this orbital. So if there's 2 electrons here and 2 electrons here, this would be 1s2, 2s2, and this would be beryllium. Okay? Each s only has one type of orbital. Notice the 2 makes me see that this orbital is bigger and farther away. So electrons jump from a what? A 1s to a 2s. They're absorbing energy. When they jump back, they emit energy. Same stuff as Bohr. It's quantized, except now we're dealing with these three-dimensional wave functions. Okay? Here comes the 2 p's. The p's generally a little farther away from the s. And you notice there's 3 different shapes. There's 3 different boxes, 3 different orbitals. This holds 2 electrons. This holds 2 electrons. This holds 2 electrons for a maximum of 6 electrons. Then 3s. Notice it's bigger than the p's. It's farther away. 3s is after the 2p. So it's a higher energy state, farther away from, I would say, Nuru or Big Mama. 2p, 3p. And p's are generally a little farther away from the s's. And you can see what's happening here. Notice there's only 3 different shapes for p's for a total of 6. Now I'm at 4s, circular again, only one shape, one orbital, one box for 4s. Now here comes the d's. How many different shapes? Oops, there's 1. There's 2. There's 3. There's 4. And there's 5 different d's, and I'm going to rotate maybe. 5 different d's, they're a little farther away from the 4s, and that's why it fills that way. Okay? And then we go back to the 4 p's, and you get that idea. Okay? Remember, there's 5 p's because there's 10 electrons. And of course, if there was f's here and there's not f in this animation, okay, they don't want to f around. Okay? So therefore, there'd be 7 shapes as I showed you before. So let's continue because we want to have some fun here. And let me make this smaller. So I'm going to view and I'm going to zoom out. View, zoom out. All right, so we can see everything. Now, the first sublevel is a 1s. Well, put an electron here, it's 1s2. Second sublevel. Well, next sublevel is still the same s, but it's 1s2. So I'm adding some electrons. Notice the arrow's going opposite. Here is 2s. Notice it's farther away from the nucleus. The nucleus is right here. First electron, lithium, 1s2, 2s1. Next electron, 2s2. And you can play with this. I have this linked to the presentation, so if you want to play with this yourself, you can. So 2p1 is a boron, don't be one. Carbon, 2p2. 2p3, notice they're going in empty orbitals first. It's called Hudd's rule. Why would they repel themselves if they can be farther away? Remember, this only works if you're in the same sublevel. Now the nitrogen is forced to pair up. Fluorine, and magic, it's filled, just like 1s2 is filled. Stable. Next, 3s. 3s1 is sodium, 3s2 magnesium. Notice it's building. This is going in order. By the way, I'm building something called ground state electron configurations. I'm starting from low energy to high energy. Next, okay, and you can see how this fills. 3p2, it's silicon, phosphorus, 3p4 sulfur. Okay, eventually, oh, argon, stable. Everything is filled. Now you know argon, it needs a D to fill, right? D's hold 10. So truthfully, argon does not has a filled third principal energy level. It only has a filled S and P, and that's okay. Even though we call this the octet rule, once the S and P are filled, there's something special about having 8. It's still very stable. Not quite as stable as the neon or helium, but very stable nonetheless. And here we go with the D's. The 4s fills first because of overlapping, as we saw today. Okay, then we have scandalous or scandium, 3d1, 3d2. Okay, now I'm going to show you something, but I'll probably have time to explain it Monday. Watch what happens here. Vanadium, you expect to fill here. But what happens is the 4s and 3d are very close in energy. And electrons would rather be what? In empty orbitals. I know I said Hudd rule states that this is only going to happen in the same orbital because 4 and s are so close in energy, the 3d's overlapping a little bit. What happens is when I hit the next electron, this is 1, 2, 3, 4, 5. I'll do it. Whoa, what just happened? Well, we put one here, and the one that was here wanted to be in an empty spot. And because the repulsion between electrons was so great, it moved there. So that's why it does that. And you don't have to know that for a test, But these electrons are finding stable states. The 4s and 3d are very, very special. Okay, and there's some overlap between them. Therefore, they're almost like the same sublevel. All right, and of course, you add the electrons, and there might be some more play going on here. Watch what happens here, the next one. Now, notice when you fill stuff, okay, it would rather be filled, and what happens here is, whoa, one came off to fill that one. Because this is a stable state. Filling all of these D's is more stable than this being individual. And again, electron-electron repulsions here made it possible for this to move. And again, the 4s and 3d are almost like the same sublevel. Okay? And again, if you don't quite get that, we'll talk more about that Monday. And here comes the 4p's, and here comes Hudd's rule, definitely. And there's no play between these two because these are really far away in energy. Okay? And so this is called orbital notation. You know they're not boxes, they're actually shapes, but you use it to show the distances and energies. So a 4p electron jumping back to a 3p is giving off energy, and a 2p going up, very important. Any case, let's go back to the periodic table. Okay, so let's look at the electron configuration of nitrogen. We go 1s2, 2s2, 2p1, 2, 3. Okay, now party people. How many valence electrons? Well, valence electrons are electrons that are not in a filled energy level. Like I told you, if you look at N, you'll see 2-5. 2 is for the electrons in the first energy level, 5 is for the second, so 2-5. Now, this is special. This is filled. This is called a core electron or a kernel. These are not available for bonding. But this has 5 electrons. And because valence electrons are electrons available for bonding, you'd count both of these. It's the outermost electrons. So there's 5. Notice it's group 15. Take the 1 away. Look at oxygen. It's 2-6. What does that mean? 1s2, that's the 2 electrons. Then the 6 comes from the what? 2s2, 2p, well, what? 1, 2, 3, 4. And you can see that 6 comes from the outermost shell, or electrons. I don't care if it's 2 or more different sublevels. This is the kernel, not available for bonding. So that's very important. Now, so you can just look at the last number. Lithium has 1 valence, sodium has 1 valence, K has 1 valence. Hey, it's group 1. These guys have 2 valence electrons. Very important. These guys have 7. You can see the difference, the last numbers. Now, the only little difference here is with transitional elements. And just as I told you before, because these elements, the S, this is the 3D, right? And this is the 4S, because of overlapping, okay? This 4S and 3D are very similar in energy, but the 4S in this case is a little closer, a little lower in energy, so it fills first. Now, when we look for a valence electron, because the 4S and 3D are in fact almost the same energy, valence electrons for these d orbital atoms called transitional metals. Transitional metals, I'm trying to write. They're transitioning, okay? They're special kind of metals. Their valence electrons are from the S and the D. So what I mean by that is, if I write the configuration of scandium, I'm going to write it right here. You can look at your periodic table if you need it. 1s, oops, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Now, what's its valence electrons? Well, these are core electrons, right? That's filled. This is filled. Oops, not good. All right, let's go back down, sorry. So let's go here. So this is filled. Now what's not filled, okay, is the 3 and the 4. So you're kind of confused. What are my valence electrons? Well, didn't I tell you that filling the S and the P makes it stable? Although that's not a filled energy level, this is a very stable zone here. Okay, if you look at 3p6, who is that element? 3p6, okay, is your argon. So argon's core is very stable. So believe it or not, because I can write this configuration, and if I was asking to write the configuration of scandium, you'd write it this way. But you can also use a shorthand notation. Scandium can be written like this. Again, who is 1s2, 2s2, 2p6, 3s2, 3p6, which we know is very stable? It's argon. So I can do this. Argon, brackets, 4s2, 3d1. Yeah, I can do that because those are the stable electrons. All right? That's a shorthand notation. Now, my question to you is, what electrons are outside that stability zone? And you would say there's 3 of them. That's why scandium has 3 valence electrons. And this is very important. It has electrons from 2 different energy levels. Everybody else gets electrons from 1 energy level. Magnesium's 2-8-2. These 2 electrons come from the 3rd. Okay? But these guys get their valence electrons from 2 different energy levels. Titanium, okay, is 4s2, 3d2. So it has a total of 4 valence electrons from 2 different energy levels. And that's why they put the 4 here. Vanadium. Notice scandium becomes +3. It can lose 3. Titanium can lose 4. Vanadium, okay, would be losing 5. Chromium 6. Magnesium 7. Now, over here it doesn't happen as much, and we'll talk about that Monday. All right, but generally speaking, you can gain your valence electrons from these guys from their 2 different energy levels that are very close in energy because of that overlapping. Okay, that's important. Now, let's continue with the last piece of this, excited versus ground state. All right, let's make this white. It'll be all white. And this is the last little piece, and I'll be finished. This just became a long lesson. I feel bad, but now I'm over it. Okay, so here we go. Let me draw, let's say, 1s2, 2s2, 2p3. What element is that? You may say, well, how do I know that? I'm going to do this 2 ways. 2-5 and look that up. And if you look that up, that's nitrogen. Or count the electrons. 2 plus 2 plus 3, okay, is 7. Who has 7 electrons? Remember, these are not ions. These are atoms. So the electrons equal the number of protons. Okay, now this is a nitrogen. So nitrogen is in the ground state as written. Why? Because I am not excited. Now, ground state configurations, this is very important. Ground state means that electrons are filling from lower energy orbits first, just like I showed you with the orbital notation. The 1s is closer to the nucleus. In fact, when you write it this way, you might want to what? Notice that the nucleus is over here. And notice the 1s is closer. And that's how we do it. Now, it's in the ground state because it's filling lower energy levels first before it fills higher energy levels. But what if I was to write this? 1s1, 2s2, 2p4. If you notice, 4 plus 2 plus 1 is 7 electrons, and that's also nitrogen. These are both nitrogen. But this is not going in order. This is called an excited state. We should know what this is about. That means that an electron closer, that one of these electrons in the s jumped, made a quantum leap to the 2p, and the resulting was that I've got an electron. I call this a missing hole, and this is an excited state. Excited states will show electrons going out of order. It doesn't mean that you have a wrong number of electrons, because if I give you 2 excited states and say, hey, which one is oxygen or nitrogen, you can count the electrons to know what you have. For instance, here's oxygen. 1s2, 2s2, 2p4. It's the same one as this one. No, it isn't. It's 1s2. 2 plus 2 is 4. 4 plus 4 is 8. Atomic number 8 is oxygen. Okay, so this is definitely oxygen. And guess what, my friends? It's the ground state. Why? It's going in order. What could I write to show an example of an excited state? Well, how about this one? 1s2, 2s1, 2p5, going out of order. This can't be filled until this one's filled. So this is showing a missing electron that somehow in the process jumped from here to here. And when you jump away from the what? The nucleus is which is always in front. Think of the nucleus always in front. Energy is absorbed. You should know that. Energy is, in order for Nuru to get to a high energy state, he has to gain energy. Okay? Now to jump back, When the excited state comes back to the ground state, that's when the energy is released in the form of light that we talked about. So you have to know that. So the excited state is that unstable Mr. Unstable I showed you. Electrons gained energy from a low energy orbit, or low energy orbital, I should say. And you should notice orbital sounds a lot like orbit, and that's because quantum mechanics gave credit to what? Niels Bohr orbits. That's where this started from. Okay, so to identify excited states, we're looking for the missing. Now, sometimes this gets a little tricky. For instance, if I was to draw this example right here, let's go 1s2, 2s2, 3p1. And I say, is that a ground state? Is that going in order, or is that an excited state? And we'll say, well, it looks like it's going in order. 1s2, I don't see anything missing here. But wait a minute. 3p1, shouldn't that be 1s2, 2s2, 2p1? Yeah, so an electron jumped from the 2p to the 3p, and it gained energy and it got excited. So this is an excited state configuration. You say, of who? Count the electrons, right? 2 plus 2 is 4, 5. And who has 5? Oops, that's crazy. Who has 5? This is the excited state configuration of boron. Careful, okay? You're not gaining or losing electrons. All right, now, of course, if you have ions, they equal the noble gases. We did that today. All right, any case, that's all I wanted to show you today. All right, hope that helped, and this should be able to complete the sheet.